talk about hypergraph simulations.
Okay, thanks very much, Chris, and thanks for the opportunity to talk. Okay, so this is a joint work with Fabrizio, who's somebody else's PhD student in my group who I've been messing around with this stuff on. This is new stuff, so big disclaimer up front. I've not explained this before to a sort of a general audience, so if it comes muddled, it's not you, it's me, as they say. Okay, so the plan of attack is we're going to have a quick sketch of compact closed categories and diagrammatic calculi. That won't take very long. This audience seems very comfortable with that type of thing. And then we're going to have quite a large discussion of how you lay your hands on these compact closed categories that you can interpret your diagrammatic calculi in. And there will be several examples that are probably familiar to people, and some, in a way, kind of cheap tricks to construct a couple more, and then the question is, where does all of that stuff come from? And then the aim, hopefully I'll get there, is then to look at a sort of general framework based on generalized relations, where we can cook up an awful lot of examples of these compact closed categories. That's the plan of attack. Okay, so hopefully this is familiar to most people, but just to give us a slight handle on things and to get some pictures in an early slide. We're thinking about the sorts of symmetric monoidal categories where, well, we can always interpret this sort of diagram where we have our tensor horizontally and we have composition of morphisms vertically, and in particular we'll be interested in compact closed categories that have these nice cups and caps that let us bend wires, and they have a couple of snake equations like this one that let us basically pull the kinks out of the wires, and that leads to a very nice diagrammatic calculi that you can describe quite a few different sort of computational and physical and other phenomena in, so it's a nice setting to work in. Okay, so some examples of compact closed categories and where they're used. So kind of the canonical one, if you're physically minded, is the category of finite dimensional Hilbert spaces. That has a nice compact closed structure, and that's a setting you would do pure state quantum mechanics in, or at least the finite dimensional fragment of it. So that one crops up an awful lot. There's an awful lot of papers analysing that setting. There is then the category given by Salinger's CPM construction of completely Hilbert spaces and completely positive maps, and there are some variations on this construction, which you can think of as a setting for mixed state quantum mechanics. So that's where you've got partial or incomplete information. So those two are the two sort of physically motivated things. And then REL, which has already cropped up, which is good because that's warmed me up, because I'm going to be banging on about various versions of REL all the way through here. That's sometimes used as a toy example or as a counter model when you're looking at these compositional theories of physics and various other things, so that one's another commonplace thing. Then we get into some sort of weirder stuff. So co-spans are not too weird. Correlations are kind of the jewel of relations, and I'm not going to explain those well now. They're not relevant for what comes up later. And we'll talk about those in a little bit more detail on the next couple of slides. And then there's also this well-known span construction that will cook you up a compact closed category in a fairly easy way as well. So the question is, can we find more than these? Because it's a sort of limited repertoire of tricks that we've got that we can cook these things up with. And it's not clear how to cook up particular categories with particular properties that you can do these types of calculations. Okay, so there are a couple of procedures that allow you to cook up new compact closed categories from old ones or from a set of parameters. So one of them is Salinger's CPM construction. So as I mentioned earlier, that takes pure state quantum mechanics and outcomes mixed state quantum mechanics. But it's kind of a very disappointing procedure in a way. You can always do this thing, but outside of the quantum setting, an intuitive answer as to what the heck it's doing is quite hard to lay your hands on. So there's some literature a while ago, and there was a sort of general sense that this was sort of a mixing construction somehow, and you could apply it to something like the category of relations and you get mixed relations. But a bit more inspection of that claim suggested it's not actually true. In that case, it has a very combinatorial feel and doesn't feel anything like mixing. So this is kind of not the sort of procedure we want. We don't want something where we haven't got a good handle on what it's going to produce, because we want to be able to figure out how to produce into the nice properties that we're aiming for. So that's not really the plan. Okay, so a slightly better candidate, or probably a lot better candidate, are these categories of decorated correlations and decorated co-spans. So this is work of Brendan Fong, who was formerly in Oxford and now, not sure, somewhere in the US, that I'll hopefully remember later. And they're rather nice constructions that they generate in a way they're completely generic for a certain class of these compact closed categories. They generate them all. So from that point of view, they're pretty comprehensive. But they're parameterized in a rather technical way by things like factorization systems and lax-monoidal functors, which that might not be the first thing that comes into your head when you're thinking about how to build yourself a compact closed category. So then that basically means that you're going to require a certain amount of cunning to figure out how to encode a particular thing into the setting that Brendan describes. But the good news is that if it's possible, then you can always do it with Brendan's construction. It's completely generic. Okay, so now on to some weird stuff. Most of what I mentioned in my talk seems to have been mentioned already. Someone's mentioned symmetric monoidal categories, we've mentioned compact closure, we've mentioned monads, we've even mentioned graded monoids or ordered monoids and various other things. And topos is cropped up as well. But nobody has mentioned mathematical models of cognition. I thought I might at least have the exclusive on that one. So yeah, that's straying from the current path. So this is something we've been talking about in our group, and from you guys' point of view, if you want to not pretend I'm a crackpot, just think quickly that our motivation is similar to the physics motivation. We kind of have subsystems or sort of ways of reasoning, and we want to combine them together into larger things that we might be representing in our head. The details are slightly unimportant. So in particular, we've been looking at work of this guy, who I'm going to pronounce Gardenforce. It isn't pronounced that way, and I apologise to anyone that knows how to pronounce that correctly, but we've just called it that so often I can't fix it now. And his models are described, they're kind of described in a sort of pre-mathematical way. He has a mathematical description of what goes on, but it's imprecise and there's quite a lot of wriggle room in terms of how you should interpret it. And we've been looking at how we could produce a compositional version of his theory. And in particular, he emphasises convexity as a sort of important notion that should be available in a model of cognition. So the idea here, very intuitively, is you kind of have a space of descriptions of things in your head, and if this is a dog, and this is a dog, then things in the middle should be dogs as well. So that's where the convexity comes in, all very scientific. Well, that's kind of the idea. Things in between should be similar to the things on the endpoint. Okay, so how are we going to get this important convexity notion involved in some sort of compact closed setting? So the way we did this originally is just someone in our group is obsessed with monads, so monads sprung to mind quite quickly. And in particular, the distribution monad, which probably this is familiar to most people here, basically sends a set to the finite probability distributions over discrete probability distributions. And if you look at the Eilenberg-Moore algebras of that monad, they're basically sets with a thing that takes a convex mixture and produces you a new element. So they're convex algebras is the name for these things, and they've got a mixing operation on them. So that kind of sounds encouraging that we can get our handle on some sort of notion of mixing. So this category isn't compact closed, but now we can use a sort of second sort of standardish trick. We know that this Eilenberg-Moore category is going to be regular, so we can form its category of relations. And that's going to give us a compact closed category, and the relations in there are going to satisfy this equation here, which basically says if you've got related bits, that's how you should read the left-hand side, then when you mix the bits together using the same mixing procedure, then you'll get related bits as well. So that's roughly what you're going to see there, or exactly what you can see there. Okay, so the cognition crowd, as I've said, they're kind of pre-mathematical in the way that they describe things, so you kind of have to dig through what they're talking about and then see what's involved. So they often talk about distances and things as well. So you can imagine the idea here, if this is a dog and this is a squirrel, they're kind of nearer than a dog and a functor might be in terms of how you might describe them. So you kind of need to be able to measure things, and they talk about distances in various ways. So we want to get our hands on metrics. But the obvious categories of metric spaces that you might choose, they're not regular, so they certainly don't come from one of these algebraic constructions. So we can't use the cheap trick that we used on the previous slide to try and produce ourselves a compact closed category this time, so we're going to have to be a bit more creative and come up with something else. So again in a rather ad hoc way, based on the random readings of somebody in the group. So this is kind of all luck in a way that you happen to know the right tricks. We found that if we use quantiles in a certain way, we can get things done. So we're going to take a little detour and just quickly describe what quantile is, because that's going to take us in the right direction. So unital quantile is a set with a binary operation on it, so a monoid structure on it, so a binary operation and a unit, which I'm going to write as a tensor in K, because that's just the notation we happen to use. So you can think of these things as a special case of monoidal categories. And it also has a join operation such that the monoid structure is a homomorphism for that in both components, so these axioms hold. And if we're given a quantile, we can define ourselves a category of relations, where a relation is basically a thing that takes, an element in set A, an element in set B, if we're thinking in terms of sets at this point, and gives you a truth value for how related they are. So the quantile is going to serve as truth values in the way that we're constructing things. So this is all well-known stuff so far. We're just using things that happen to be around. And we compose things by basically figuring out all the ways we can go from A to B and then B to C, tensoring them together because the quantile gives us the necessary sort of finite tree operation to combine those guys, and then picking the best one via the join. That's how you can read that. Or you can think about it in terms of multiplying big matrices is another way of thinking about this. And we're going to refer to these guys as Q relations. It's a bit easier to say than Q value relations. And if our quantile is commutative, then we get a compact closed category. So we're slightly along the way, at least, that we've found ourselves another compact closed category. But we haven't answered the question about what the heck this has got to do with metrics. Yeah, that's to come. So we also noticed that this category rel Q is...
Sorry, what's the base category, sorry, in the previous slide?
So base category, we're basically thinking of set to quantile mappings here. So that's all we're building. See, I'm not sure I can think of a base category of this, but it's kind of built on top of sets, and then we're building these relations that map into a quantile. So there's you've only got one parameter effective at this one. There's an ordinary quantile in the sense of sets with structure. Okay, so we can order things basically using the order structure that we have on our quantile in an analogue of the usual way that you would order relations pointwise. And this gives us a poset enrichment on our category of relations. So we can then talk about internal monads in these categories, or two categories it is now, which we've done a little bit of that earlier, fortunately, everything seems to be repeating. And in concrete terms, what that means is that the identity relation is contained within another, inside our endo relation R, and our endo relation R combined with itself is contained within itself. So kind of a transitivity and reflexivity condition. How to look at that. And just in case it's not obvious and as it's getting into the afternoon, the reason this is an internal monad is we think about the normal monad axiom, stick a double arrow there, if it's sloppy on me, and you can kind of see how these things parallel each other. And because our two categories are thin, we don't have multiple arrows, we don't have any axioms to check. There would be axioms down here, but they don't really affect anything up here. Okay, so finally we can get to how this gets us to metrics. So if we look at the quantile of just the Boolean truth values, and then we look at what an internal monad is in that category of relations, well, it has this reflexivity and transitivity conditions of what fall out. So basically we've got pre-order there. So it kind of gives us a sort of structured object in our category in quite a nice way, where we've got an order on things, which might be a useful thing to be able to get your hands on. If we take our quantile to be the unit interval with the obvious sort of join and meet on it as our quantile structure, then we get something that looks kind of like a fuzzy pre-order. So this one's kind of a bit of a reach, but basically you're maximally related to yourself, and if you can get from A to B and B to C, then you'll be at least that related by going via A to C, because there might be some other way of getting there. Probably think about. Now we get onto this interesting quantile that we might care about, is if we take the closure interval from 0 to infinity, reverse the order, so we take the join in our quantile to be infimum, k to be 0, and the tensor to be plus, and we look at what the internal monads are in there. Well, the kind of generalized metric spaces. So we have that you've got zero distance to yourself, and if you take the sort of triangle equality analog, if you go from A to B and then you take the distance from B to C, that's going to be further than going directly from A to C. So that's kind of encouraging that we've found ourselves metrics in there. And if we slightly vary this quantile and replace plus with max, then we get this condition here, which is kind of a generalization of the ultrametric space condition. I hope they've got the right one. So we can get our hands on some quite interesting things here as internal monads in these categories of relations. Okay, so these two things we kind of find via sort of ad hoc tricks and cunning. So we had a trick involving regular categories and algebraic structure, and then we used a monad to sort of give ourselves a regular category that we could then do the rel construction on. And then we have this rather more ad hoc looking procedure where we take these matrices of truth values in a quantile. And so, well, the questions you might ask yourself at this point is, you know, what the heck have these things got to do with each other? Can they interact? Are they instances of the same construction? Can we do similar things and build more examples of compact class categories? And if we can get our hands on that, that looks like, you know, there's at least a couple of parameters milling around here. We have a quantile and we have some algebraic structure that we might be able to vary. Can we go a bit further in terms of generalizing things and think about how to generalize relations in different directions to give us even more parameters via which we can build compact closed categories? Okay, so a quick detour. So there's a notion of a hypergraph category, which is due to Alex Kissinger and Brendan, again, that I mentioned earlier, and possibly other people. So the idea here is you have a commutative monoid structure and a co-commutative monoid structure on every object in your category, such that the Frobenius axiom holds, the speciality axiom holds, and these guys are compatible in a sensible way with the symmetry. So basically you can glue together an A1 and a B1 to build bigger ones up, and those are going to be equal, so on the nose. And examples of these things would be the rel construction applied to the Eilenberg-Moore category of a monad, and the rel construction that we get with this quantile parameter. So it turns out actually we've been making hypergraph categories rather than arbitrary compact closed categories. So these look like probably the right thing to focus our attention on. Okay, and it turns out every hypergraph category is a dagger compact closed category by building our cups and caps out of the various bits of algebraic structure we've assumed on each object, and the dagger is just given by transposing things, which works properly because of the compatibility conditions and the description in the hypergraph category. So that's the way we're getting our hands on compact closure. Okay, so it seems probably the easiest place to start is to think about these Q-valued relations that seem quite simple. They're just matrices effectively in a way. And then see if we can do something about the algebraic structure that we would like to get into play again. So we saw this axiom earlier for that construction that we use for building relations on a regular category, where if we have a bunch of related bits, then that implies that combining those bits together using the same operation will lead to something that is related. So how do we generalize that to an arbitrary quantile? We just sort of follow our nose effectively. Instead of having ands, we're going to have to stick in tensors here. That's kind of our analog of conjunction. And then this implication's got to go as well, so we're going to use the order structure on our quantile in order to give ourselves the condition that we hope will capture the algebraic phenomenon sensibly. So we're going to refer to these as algebraic Q relations if we need a name for these things. Okay, so if we take those things as a definition, then we're going to need to be able to find ourselves some appropriate structure there so we can form a category of these guys. So in the set theoretic case, it seems fairly obvious to define the identity as relating A to itself with strength K, and otherwise relating everything else with the minimal element. So those guys aren't related at all. And to use the same composition of relations that we saw before in the case where we hadn't imposed any algebraic structure. That seems a natural thing to do. And if you're feeling a bit flash, then what you might well think at this point is, why this obsession with set as our base category. So with a little bit of a tweak on the way that we describe the identities, we can actually do this stuff with an arbitrary base topos and then an internal quantile within that topos. So that doesn't mean anything to you, just assume that everything's sets and hopefully things will make sense from here on in. But it means we've got another axis of variation via which we can build compact class categories, so that's what we're hoping for as we proceed. Okay, so it turns out if we pick ourselves a topos, an internal commutative quantile in there, and we have some algebraic signature with some equations in E, then we get a category of relations in there with objects, the algebras and the morphisms, the algebraic Q relations that we described a couple of slides ago. It has symmetric monoidal structure given by the product structure in the base category, and this category is post-set enriched as well with respect to this generalized ordering that we saw earlier, just kind of lifted up to the internal language and the internal logic. And this guy is a hypergraph category, so we found a way of churning out quite a few of these things by varying 3 different parameters, I would say, at this point. Okay, so some just hand-waving details of what goes on. The tensor just uses the quantile structure to combine the truth values together on the 2 different components in the obvious way. We need a graph construction. So if we start with an algebra homomorphism, so F, then we can turn it into a graph in the sense that you would take a graph of a function to produce yourself a relation, and we define how that relation will work in the internal logic via this fairly intuitive thing. If you think in terms of set theory, it seems to do roughly the right thing. And it turns out that this gives us an on-the-nose strict symmetric monoidal functor going from this category of algebras into our category of algebraic Q relations, which means we can transfer up the comonoid structure we get by the diagonals and the kill map. And if we take converses of those, where converse is kind of the obvious argument swapping thing, then that will give us a monoid structure as well, and then some calculation tells us that actually those objects satisfy the hypergraph condition, so that's basically where we were heading. Okay, so that's relations and a theorem related to that, and some examples that we get. Obviously rel falls out of this procedure. The rel on a quantile giving us the generalized metric spaces falls out of there. Similarly, we get the one with generalized ultrametric spaces. We get the category of convex relations that we mentioned with respect to the cognition stuff if we choose this signature and quantile appropriately. We get the category of linear relations that's used by you and Pavel and various other people, although not quite, because we also get things of infinite dimensions, so you have to take the finite dimensional part of that, but modulo that, proviso that gets churned out here as well. And we get some new things that sound like they might be worthy of investigation. So we can produce C-valued relations, but with convex structure on the objects, which gives us a notion of convexity and the internal monad to give us a type of metric that we can look at. So that is for sort of further practical investigation in terms of these possibly crazy-sounding cognition models. And then similarly, because we allowed the underlying topos to vary, we can think about taking semantics of things like language varying by context. So the context could be an agent or time or various other things as well. So that gives us some more freedom for exploration at a later date. Okay, so how long have I got? Somebody else? 50 minutes. So doing okay. Okay, so that's kind of a three degrees of freedom way of producing some complex first categories via generalized relations. So we mentioned spans earlier, and so span, just to make things concrete, is you pick data of this form, so not satisfying any axioms in particular, and we can think of these things as constructive relations, or that's one way of thinking about them. So you pick an element little x up in the apex, then we can think of that as a proof witness that f of x is related to g of x, which I'll use this informal notation for basically saying that x relates a to b And we could have multiple proof witnesses, so we can have A related to B in various different ways, which we didn't have in the algebraic setting. Okay, and spans are composed using pullbacks. This is all sort of well-known stuff. Again, we're back into conventional territory. And we want some intuition for what goes on there. We just recall what pullbacks look like in sets. So they basically take you all the pairs that meet in the middle here. That's basically what you're going to get out. So what we conclude is that the pair XY relates A to C if we can find a compatible B such that we've got this relationship there. So that's kind of how we can think of spans as being generalized relations. Okay, so then we start thinking about the structure that we saw previously, and can we sort of fold that in with the span construction as well? So we want some notion of truth values again. So we had a quantile before. At least to get going, we really only need a monoid here. So we pick some monoid Q of truth values, and then as well as the usual span data, we give ourselves a sort of little characteristic function that tells us how strong these proof witnesses are. How strongly do they witness that the two things are related in the feet of the span. And we'll again give ourselves a little bit of informal notation saying that X is relating A to B with strength Q if X is sent to A down this leg, X is sent to B down this leg, and the characteristic function tells us that the strength is Q in the obvious way. And then if we think about how composition should work, we basically use pullbacks, and then we have to do a little bit of straightforward stuff to build ourselves a new characteristic function as well. But the intuition is basically that in the obvious way, a pair XY is going to relate things with strength P times Q if we can find a compatible B and such that the things were related with strength P and Q along the two legs. So that's kind of the obvious thing. And then as a quick theorem at this point, if we just pick ourselves an internal monoid in a finitely complete category, then the Q spans form a category, and if that monoid is commutative, then we get ourselves a hypergraph category. So there seems to be this sort of slight magic of commutativity. Is you don't get that much structure until you throw in the commutativity, and then you get everything. You get to hypergraph straight away. So it seems to be important for these constructions to work. Okay, so now we want to get the algebraic structure in play as well. So how should we think of this as working? Well, again, we kind of follow our nose from what we saw from the rel construction. So if we have a bunch of things related with appropriate weights up here, so this is kind of our precondition, then we would expect that we can find another proof witness with strength Q relating their algebraic combinations on the feet, and such that this Q is at least as big as combining all the proof witnesses' weights on top. So maybe it looks fiddly, but it's basically just that rel construction generalized to incorporate these proof witnesses. And at this point we notice that, well, we can't even say this without having some order structure, at least on our monoid, otherwise this wouldn't make sense. So we're going to need partially ordered monoids, so you managed to land on that one. Everything gets mentioned at some point earlier in the day. So if we have a topos and variety in that topos, and Q, which is an internal partially ordered commutative monoid, so again this commutativity always seems to be essential, then our algebraic Q spans form a category span with the relevant parameters, and this category of spans is a hypergraph category again. So this is another generalized relations construction that allows us to cook a hypergraph category.
So here you don't have arbitrary agreement in Q?
No, you don't. You don't need that. So you're just composing using pullbacks. If you think about what you've got to do, if you're thinking about relations, then when you're looking at combining two relations, you have to pick the best way that they're related. If you think about how spans work, they're just keeping track of all the individual ways that things are related. So you only need to glue those together using the monoid structure, but then you don't need to pick the best one, so you don't need the join. That's basically the reason that you can get away with a lot less. So just a few details of the structure. The tensors are given by the products in the base category again. We have another graph-like construction, so again we follow our nose. We think these are generalized relationships, so they should have some sort of graph-like structure. If you ignore this part, this is the usual way of embedding a category into its category spans, and then we just bung on this thing that's going by the terminal object, so it's the constant thing that just sends everything to strength k, so it's kind of the obvious thing to do. And the hypergraph structure is then given by taking graphs of the diagonal and kill map again, so it's the same way that things work also. The analogy with rel seems to work really quite well. And we can put some order structure on these spans as well, and we say that this span, so this is the apex and the two legs, and the characteristic function is less than this one. If we can find a monomorphism in the base, such that things sort of factor as a span morphism in the appropriate way, and this looks quantified strangely, but basically the characteristic functions are going to sit beneath each other in the obvious way. Look, I think there's a typo there, I don't have to solve at this point. And this gives us a pre-ordered monoidal category. It doesn't seem that's going to be a partially ordered one. I haven't resolved that question yet, but it seems to be a little technical point that doesn't maybe go as far as partially ordered. And then another obvious observation we can make, which relates to Chris's question, is if our Q actually is a quantile, then we should be able to turn one of these spans into an actual genuine relation by taking the join over all of the different ways that things are related, so kind of pick the optimal thing. And we call this functor V because I'm simple-minded and it looks like the join, so that's the only way that I could tell myself remember the name of the thing. And it turns out that that works in that we get ourselves, again, a very well-behaved, strict monoidal identity on objects, identity and surjective on objects, pre-ordered functor, so it respects basically all the structure that's around on the nose, taking our spans down into relations via optimizing the choice of proof witness. And this thing commutes with taking graphs, which is kind of obvious from the way that the graph constructions work. So now, ending at about the right point, what we've got to at this point is we have a procedure for constructing new hypergraph categories, which is parameterized, at least to extent in more conceptually motivated ways than maybe the more abstract constructions. This is probably the most abstract feature, that we can pick the ambient mathematical universe and vary that. Very concretely, we can vary the truth values depending on how we want to measure how things are connected to each other. We can impose algebraic structure, which gets us things like the convexity that forces certain shapes of objects to be important. And we can choose between proof relevance versus provability in terms of whether we take the span or the rel construction, and we can relate these guys together. Okay, and then as I wrote the slides, I realised I was not going to be able to fit in lots of other stuff. So this is the catch-all slide for other things that we've managed to do so far, or are things that we're thinking about looking at. So far we've looked at this idea of having a conceptually motivated way of producing hypergraph categories using some sense of generalized relations depending on how we want to build these things. And it turns out this construction is functorial in the choice of truth value. So if you have a quantile homomorphism, you'll get a homomorphism between the categories involved. And it's farcically well behaved. It preserves all the structure on the nose, so everything's very nice there. Similarly, if you have a homomorphism of partially ordered monoids in the span case, you similarly get a farcically well behaved function between the two. So that all works out very nicely. So then I suggested to Fabrizio that we should get something similar for the algebraic situation. That turns out to be more subtle. It isn't the case that if you have sort of a homomorphism of signatures in the obvious sense, where you interpret operations in one in terms of derived terms in the other, that things will work out on the nose. And that has to do with the fact that our quantile kind of pulls us into the land of linear logic. Are we allowed to delete things or copy things when we're building these derived terms? So if you would pick the appropriate notion of interpretation for the algebraic structures, and there's basically 4 choices, then that forces you towards an appropriate one of 4 choices for the quantile structure. Or you can choose an extra one of 4 axioms that are imposed on your relations, and again, then you get a functorial relationship between these things. So it kind of depends on the nature of the various parameters you've got in play. We're also looking at the obvious bits and pieces that we're typically interested in for these things like zero objects and byproducts that we've been looking at that already. And the construction should also be functorial in the choice of topos. Me and Fabrizio aren't quite topos macho enough to have addressed that one so far. And it's actually slightly harder to sell in terms of this principal construction because it's going to vary two parameters at once. When you vary topos, obviously you're going to have to move your internal quantile at the same time. So it seems a less straightforward procedure than simply varying one of the parameters. Another observation is that this category of spans, when you actually build these categories of spans, you do a bit of quotienting as well, which I've kind of shuffled out of the way because it's just an annoying distraction. But really, our category of spans should be some sort of symmetric monoidal bicategory and then the hypergraph version of that, but that needs to some penning down as exactly what that statement means. But the reason to be interested in that, apart from sort of mathematical excitement, is this observation that internal monads in appropriate categories of spans give you small categories, for instance, so that there's other things to be interested in there. And also in that direction, if we choose our truth values, we can actually go a bit further than quantiles. We can choose to take these matrices over appropriate monoidal categories, so that gives us a bit more sort of lifting power. But that's more technical and possibly harder to follow. But the conjecture there is that in the case that these monoidal categories are symmetric, we should still get a hypergraph category, and that would also point us in the direction of Lack's observation. It probably goes back further now, but Lack is the one aware. Okay, so that's kind of everything.
So what you're doing, I think, is extremely related to Cartesian bicategories,
Yeah.
by carbonium water. So you were aware.
Yeah, I'm aware of that stuff.
Okay.
Yeah.
Because yeah, I mean, these hypergraph categories, essentially they are like the one categorical version of a
Yeah, sort of tamed
bicategory.
version of one of those. And in the case where you have a regular category, things get very tame, I think, which is in that paper as well. So yeah, the question I suppose we addressed is that there are things like the work of Carbonic Walters, and there's this sort of well-known thing that you can form categories of relations on a regular category, and the fact that monads give you these things, and then also things like spans can be seen as generalized relations, and then how do these things fit together into a coherent picture in which we have, well, effectively this is Bob, I'm afraid, but Bob insists I say levers at this point to make it more intuitive, but basically 4 things that we can vary in order to sort of configure our compact closed category in a sort of hopefully reasonably principled way, rather than having to start from, I need a monoidal category and a lax monoidal functor to do decorations in terms of the decorated span construction, for instance, which to me seems harder in principle.
Okay. Yeah, I mean, I don't know your work enough to say, but since you are aware of it, it's fine. I was just wondering if, because really looked very related.
Yeah, it's certainly in the same ballpark in terms of the structure I was looking at. Yeah.
And just another little thing is, I mean, in the beginning you mentioned how to build a compact closed category, and the first example that comes to my mind, which was not there, is geometry of interaction. You start with a trace monoidal category, build a compact closed one.
Yeah.
So does this fit in any sense with this construction that I'm doing? Or you
I'm going to be as optimistic as to say don't know at this point, because I don't know enough to answer that precisely. Maybe I should look. I'll look.
This is actually related to the Carboni thing, but I guess I didn't explicitly see an analog of profunctors here.
That, again, I've not looked at, no, but yeah, there should be something to look at there.
Because that includes almost every...
Yeah, well, that's also a question of sort of sweet spot, because things like knowing I could parameterize over a monoidal category, but we've steered clear of that. We're kind of trying to hit a point where you can configure things as you want, and this is kind of related to how we've used the procedure. And then probably there's extra questions of sort of maximum generality and how far you can take things, which I think would probably move me away from the sweet spot I'm currently aiming at, but would certainly be interesting.
So, first of all, I just want to check I understood the definition of it. So, hypergraph category is this symmetric model category with a distinguished special Frobenius, community special Frobenius algebra for each object.
Plus the obvious thing that if you have blah,
Right,
blah, that
yeah.
equals the crossover one
Sure.
here, and similarly for the comonoid
Sure.
as well. But yeah, that's basically it. Yeah.
Okay, so what you're saying, for every category, closed category that arises to this construction, you can find that distinguished Frobenius algebra.
Yes, you have a particular one that you can identify, which is this one that's given by the diagonal map, and well, basically taking graphs of the diagonal maps and the Gill map, and then taking the converses of those, and it turns out in every case that these guys, everything works out.
Now,
Nice.
does this work for categories like finite-dimensional Hilbert spaces where there isn't a distinguished one naturally?
No idea in that case, because that's just, my construction is only working for these generalized categories of relations, so I don't know how that relates to the like the Hilbert space construction is outside of our scope.
I
So.
think Kevin can fix this. I think it's also true for round, isn't it? Not distinguished Frobenius algebra, anyway.
For each object, no.
So what's the question here? Sorry.
So your construction is picking out a given Frobenius algebra for every
Yeah.
object. I think I'm wondering, how does it know which one to pick, right? 'Cause
You
it's
can
not
do
always
that in
obvious
rel
sense.
because you're kind of forced. You think about like say you're doing rel over sets, then you're kind of forced as to what the diagonal, the comonoid structure is that you're going to lift up, because as mentioned again earlier, there's kind of only one choice. You have this diagonal map. That's the only thing that's going to give you a commutative comonoid. If you lift that up by the graph construction, that's going to give you compatible commutative comonoids on everything. You take daggers, that's going to at least take you as far as having commutative monoids on everything as well, and they have that crisscross compatibility condition just via what goes on in the base, and then you just have to show that you have the Frobenius axiom holding, and that goes through for reasons I don't quite grasp. I don't have a high-level reason for why that holds, but that holds via calculation. Is kind of the best I can say at that point.
Okay.
So sort of properties of pullbacks make one way of looking at this. Sorry, so one last thing if I've got time is we have a sort of category of spans here for some sigma E, Q, and maybe we've chosen our topos as well. And if we have hypergraph structure up here, we can transfer that down to rel, blah, blah, blah. So assuming this guy is a quantile, and then if we look at span of sigma E for the sort of terminal quantile, so we can kind of ignore the truth values. So this guy's getting pretty trivial at this point. Then if we can put a hypergraph structure on here, we get a functor that transfers it all over here because it's identity and surjective on objects, and then we can transfer it all down here. So in a way, you kind of only need to confirm it in this one place and then transfer it everywhere else. And well, we've actually done the calculations at each point, but one way of looking at it is sort of via this principle. You can transfer it from this one over here via these kind of farcically well-behaved functors that have been everything everywhere. So effectively, these guys are what Alex and Brendan would call hypergraph functors, because they present the structure on their own.
Now, one more thing. So, can you recognize when a compact closed category is one of these?
No, that should be like a bullet point beyond the bullet points I've got so far. But yeah, characterizing which ones, because I'd be amazed if I generate everything that Brendan generates. I think that just isn't going to be true. So yeah, then there is a question of characterizing which of the hypergraph categories I actually can generate by the
Maybe some off-topic question. On 3 or 4 occasions you mentioned someone in that group is obsessed with modeling. Someone is randomly reading out this, and that's where the 4 parameters come in. The person happens to be you.
He's wearing my t-shirt and stood directly in front of you. Yeah.
Thank you very much.